Hi everyone. Today we are going to talk about views in this lecture. In in this video, let's talk about views in SQL today and how they help us control what data certain users can see. Imagine you are in charge of a university database. You have detailed information about all instructors, like their names, departments, and salaries. Now, not everyone in the university needs to access to all this information. For example, a student might need to know their professor's name and department, but they don't need to see their professor's salary, right? Here's where SQL views come in handy. A view is like a virtual table, an abstraction of data. It allows us to present only part of the data stored in the database. You can think of it as a window that only shows what you want specific users to see. Let's say we want to create a view where students can see the instructor's name and department, but not their salary. We can do this with a simple SQL query. Now, when students query the database through this view, they will only see the instructor's name and department, but not any salary information. Um, think of think about an HR system in a company. Employees might see their name and job title, but only HR should have access to everyone's salary data. We can use views to hide salary information from regular employees while allowing HR to see it all. Let's get into how we define a view in SQL. The basic syntax is quite simple. We use the create view statement, which looks like this. Create view as, create view v as, and the query expression. In this syntax, v is the name we give to the view, and the query expression is any valid SQL query. Once a view is created, you can think of it as a virtual table or a virtual relation, which means the view itself doesn't store data like a normal table. Instead, it stores an expression and a query that gets executed whenever you refer to the view. For example, let's say we want to create a view that shows the ID, name, and department of instructors, but not their salaries. We can do this by create view instructor as select ID, name, department name from instructor. Now, if anyone queries this view, select everything or asterisk from instructor view. They will only see the instructor's ID, name, and department. But remember, the view is not actually storing any data. It is just an expression. And when someone queries the view, SQL will substitute the expression behind the scenes and return the results. So as a view isn't a separate table with its own data. It's more like a shortcut, a way to show specific data depending on what you want users to see. For example, in a banking system, customers might only see their account balance and not all the internal transaction details or other sensitive data. Using views makes it possible to control what data different users see without duplicating or exposing unnecessary information. Let's walk through some more examples of using views in SQL. Views allow us to simplify access to data and also hide certain details when needed. First, let's say we want to create a view that shows information about instructor, but without displaying their salary. We can create a view like this. Create view as faculty. Create view faculty as, and then you have the query that is select ID, name, department name from instructor. Now, anyone using this view will only see the ID, name, and department name columns. The salary column is hidden from view. Now that we have this faculty view, we can run queries on it just like we would on a table. For example, if we want to find all instructors who belong to the biology department, we could run the query select name from faculty where department name equals to biology. The query will not return the name of instructors from the query will only return the names of instructors from the biology department without showing their salaries or other information. Creating a view for department salary totals sometimes we want to aggregate data to get useful insights. For example, we might want to see the total salary for each department. Here's how we can we can create a view to show that. Create view department total salary, department name and total salary as, and then we have the internal query select department name sum salary from instructors group by department name. This view department total salary will show the total salary for each department. Whenever someone queries this view, it will only give them the aggregated salary for every department in the system. You can define one view using another view. For example, if we already have a view called faculty that shows instructors' names and department, we could create a new view based on it. Let's say we want to view that only shows faculty from the science department. So we can say create view science faculty as select name department name from faculty where department name in biology, chemistry, and physics. Uh, so here, science faculty is defined using faculty. This means science faculty depends on the faculty view because it uses it in the query. So we say that a view v1 depends directly on another view v2 if v2 is used in the definition of v1, like how science faculty directly depends on faculty view. A view v1 depends indirectly on another view v2 if there is a chain of views. For example, if I had a view faculty salaries based on department total salary, which itself is based on instructor table, faculty salaries would depend indirectly on instructor. This is useful when we want to build up complex data layers but keep the system flexible. A view is said to be recursive if it depends on itself, either directly or through a chain of dependencies. While we don't use recursive views often in basic scenarios, they can be helpful for solving certain types of problem, like managing hierarchical structures where you want to define relationships between levels of levels in an organization. For example, in some database, recursive views might be used to represent employee hierarchies where an employee can be a manager of other employees and you want to find everyone under a specific manager. Let's look into an example where we create views based on other views. This is powerful technique that allows us to allows us to build on previous queries and create more specific to filtered data sets. Imagine we want to create a view that shows all physics courses offered in the fall semester of 2017. The view should include the course ID, section ID, building, and room number. We can define it like this. Create view physics fall 2017 as select, then the query course.course ID, section ID, building, room number from course, section, where course.course ID equals to section.section ID, and course department is physics. Section semester is fall, and section year is 2017. And now this view physics fall 2017 now holds information about all physics courses that took place in the fall 2017 along with their location. Now let's see, we want to create another view, but this time only for the course that were held in the Watson building. We can do this by defining a new view based on the physics fall 2017 view. So create view physics fall 2017 Watson as select course ID room number from physics fall 2017 where building was Watson. Here the physics fall 2017 Watson view depends on physics fall 2017 view. It filters down the data to only show courses that took place in the Watson building during fall 2017. We don't have to rewrite the entire query. Instead, we just reuse the previous view to make our lives easier and keep things more organized. Let's expand the physics fall 2017 Watson view so that we don't rely on the previous view and include all the necessary details in one go. In the previous example, we created the physics fall 2017 Watson view using data from another view, physics fall 2017. But what if we want to define the entire view in one place without depending on physics fall 2017? So this is the original view. Create view physics fall 2017 Watson as select course ID room number from physics fall 2017 where building equals to Watson. And now this depends on physics fall 2017 view, which holds the list of physics courses in fall 2017. Now let's define everything directly within the physics fall 2017 Watson view. Create view physics fall 2017 Watson as select course ID room number from select course ID building room number from course section where course.course ID equals to section.course ID and course department name equals to physics and section semester equals to fall and section year is 2017 as physics fall 2017 data where building equals to Watson. Here we have nested the query that originally created physics fall 2017 inside the view definition of fall 2017 Watson. This way, we are directly pulling the data we need from both the course and section tables without depending on another view. The inner query retrieves all physics courses from fall 2017, and then outer query filters the data to only show courses that were held in 27 in Watson building. When we create a view that relies on another view, SQL needs to expand the query to understand what data should actually be retrieved. This process is called view expansion. Here's how it works. SQL looks at the view definition, and then if the view refers to another view, SQL replaces that view reference with the actual expression that defines the second view. It repeats this process until no other view relations are present in the query. This means that SQL keeps expanding each view reference until it arrives at base tables, the real data stored in the database. Let's say we have a view v1 defined as create view v1 as select name, department name from instructor where department name equals to physics. Now we create another view v2 that depends on v1. Create view v2 as select from v1, select name from v1. When we run a query on v2, SQL will perform view expansion by submitting the v1 definition into the v2 query. So the query will be like select asterisk from v2 will expand to select name from select name, department name from instructor where department name is physics. So the expansion process continues until no more views are left in the expansion. As long as the views are not recursive, the process will eventually terminate, meaning it will stop once all views reference are resolved. Now let's talk about another important concept in database, materialized views. So far, we have seen that views are virtual relations, meaning they don't store data themselves. They just store the query that defines them. But in some cases, it is useful to store the actual result of the view physically in the database. This is what we call a materialized view. A regular view runs the query every time you ask for data. It doesn't store the result, which means it is always up to date. A materialized view, on the other hand, stores the result of the query physically in the database. This can make retrieving data faster because the query doesn't have to be re-executed each time. However, there is a trade-off. When the underlying data changes, say a table that the view depends on is updated, the materialized view can become out of date. This means the data it holds is no longer accurate compared to the current state of the database. To solve these, materialized views needs to be maintained. That means whenever the data in the underlying table is updated, the materialized views needs to be updated as well. This can be done automatically by the database system, or it can be done manually by the database administrator. Let's look at what happens when you try to insert data into a view. We'll use the faculty view we defined earlier, which contains ID, name, and department name, but does not include the salary field. Suppose we want to insert a new instructor into the faculty view. Here's the SQL query. It should be like insert into faculty values 30765 green music. This looks like a simple insertion, but remember that the faculty view is based on the instructor table, which also contains the salary column. The challenge here is that our view does not show the salary column, but the underlying table still requires it. So two possible approaches, reject and insert. Our approach is to simply reject the insertion since the faculty view doesn't provide all the necessary information like the salary. The database could prevent this insert from happening altogether. This is often the default behavior in many systems because allowing incomplete data could lead inconsistencies. And the second approach is allow the insert with null values. Another approach where it is allowed to insertion but set the missing salary field to null. In this case, the database would insert the following tuple into the instructor table: 30765 green music, then null. Here we have the new instructor green in the music department, but the salary is left as null. This might be acceptable depending on your database design and whether null values are allowed in the salary column. This issue arises because the faculty view is a subset of the instructor table, while the view inside certain columns like salary and the underlying table still expects all the columns to be filled out. So we either need to provide all necessary values or let the system handle missing data. Now let's explore what happens when we try to insert data into a view that joins multiple tables. In this example, we have the instructor info view, which combines data from both the instructor and the department tables. So create view instructor info as select ID, name, building from instructor department, where instructor.department name equals to department.department name. This view shows the instructor's ID, name, and the building where the department is located. Let's say we try to insert a new record for an instructor named White into this view. Insert into instructor info values 69987 White Taylor. This query attempts to insert new instructor with ID 69987, name White, and department located in the Taylor building. But here's where we run into some issues. Which department if multiple departments are in Taylor? If the Taylor building houses multiple departments, it's unclear which department the new instructor White belongs to. For example, if both the physics and biology departments are in Taylor, the system has no way of knowing which department to assign to this instructor. This ambiguity means the insert cannot proceed without additional information. And then what if no department is in Taylor? If no department is located in the Taylor building, the system doesn't have a match record in the department table to assign a department name for the new instructor. This could lead to a failure or a rejection in the insert because the view depends on the relationship between instructor and department. Since the instructor info view relies on the condition instructor.department name equals to department.department name, if there is no department in the Taylor building, this insertion can be processed correctly. So possible solutions: option 1, provide more information; option 2, ensure data consistency. Let's consider what happens when we create a view for all instructors in the history department and then try to insert an instructor who doesn't belong to history. So this is the query where we create the history instructor view. Now, let's say we try to insert the table following record into this view. So insert into history instructor values 25556, 6, Brown, biology, and then the salary. Here's we're trying to add an instructor named Brown with this ID at Department of Biology, and the salary is this. But this insert violates the logic of the view. Let's break down what happens. Department mismatch. The view history instructor only includes instructors from the history department. However, the record we are trying to insert has a department name of biology. Since the view is filtered to only show the history department members, trying to insert someone from biology contradicts the view's condition. As a result, this insert will likely be rejected by the database system. Insert cannot be reflected in the base table. In the underlying table is instructor table, which holds instructors from all departments. But since this view is specifically filtered for the history department, inserting a biology instructor would violate the view's constraints. Most of the systems won't allow an insert that violates the view's filtering conditions. So the database will throw an error. So the possible solution, if you want to add an instructor to the biology department, you should directly insert the record into the instructor table instead of inserting into the view. When working with views in SQL, it's important to understand when you can and cannot update the data in a view. Most SQL implementations have a specific rules for allowing updates on views, especially when the view is based on more complex queries. SQL typically allows updates only on simple views. These are views that meet a few important criteria. Number 1, single table in the from clause. The view must be based on just one table. If the from clause includes joins or multiple tables, the system won't allow updates because it can't be sure how to modify data across multiple tables. Then number 2, attribute only in the select clause. The select clause of the view should only include direct column names from the base table. It cannot include expression like name, department name, aggregate functions like sum, count, or distinct keywords. These types of operation make the view non-adaptable. Number 3, attribute not listed in the view. Any attribute that are not listed in the select clause can be set to null during an insert. For example, if a view exclude the salary column, the system cannot insert a record with a null value for salary. No group by or having clause. The view cannot contain a group by or having clause. These clauses aggregate data, and it's not clear how the system should handle updates in such cases. These rules are in place because SQL needs to be able to translate any changes to the view back into the changes to the base table. If the view is too complex, like when it's based on multiple tables or use aggregates, it becomes unclear how those changes should be reflected in the underlying data. Now let's talk about transaction in SQL. A transaction is a sequence of one or more SQL queries or updates that are executed together as a unit of work. When you execute a SQL statement, a transaction begins automatically. A transaction continues until it is explicitly ended using one of two commands. Commit work, this makes all the changes made by the transaction permanent in the database, or rollback work. This undoes all changes made during the transaction as if they never happened. So atomic transactions. Transaction is atomic, meaning it is either fully completed or fully undone. If any part of the transaction fails, the whole transaction is rolled back to ensure the database is not left in an inconsistent state. Then isolation. Each transaction is isolated from others. That means transactions running at the same time won't interfere with each other, keeping data consistent. Let's talk about integrity constraints in database. These are rules that help protect data and make sure that the changes to database don't cause data inconsistencies. They act like safeguards. Balance constraint for a checking account. Suppose we want to ensure that any checking account must always have a balance of more than $10,000. This prevents accidental entries that would lower the balance below this threshold. Minimum salary for bank employees. A rule might require that salary of a bank employee must be at least $4 an hour. This ensures employees are paid a fair wage and prevents accidental entries of extremely low salaries. And then non-null phone number for customers. We can also enforce that a customer must have a phone number, meaning the phone number field cannot be null. This ensures that we always have a contact information for every customer. Why use integrity constraints? These constraints protect the consistency of the database. These prevent accidental data loss or invalid data from being entered. So SQL constraints that help ensure data integrity, not null. The constraint ensures that the column cannot have a null value. For example, a customer's phone number might have not null constraint to make sure the phone number is always provided. The primary key constraint uniquely identifies each row in a table. No two rows can have the same value for the primary key, and it cannot be null. For example, the ID column for employees would be a primary key. The unique constraint ensures that all values in a column are different. It's similar to the primary key, but the table can have more than one unique column. For example, an email address might be a unique for each customer. And then the check constraint allows you to enforce a condition on the values in a column. For example, you might check that a salary is greater than or equal to $4 an hour. Declaring not null columns. For example, let's say we are creating a table and we want to make sure that both the name and budget fields must always have values. Here's how we can declare them. Name varchar 20 not null, budget numeric 12 to not null. The name column is defined as a variable character field with maximum length of 20 characters and it cannot be null. The budget column is numeric field with up to 12 digits, including 2 decimal places, and it also cannot be null. This ensures that when data is inserted into a table, values must always be provided for both the name and budget columns. Not null helps enforce data completeness by preventing missing or undefined values in important columns. The unique constraints ensures that the combination of values in a specified columns must be unique across all rows in the table. You can apply the unique constraint to one or more columns, and this combination acts like a candidate key. So unique A1, A2, AM, this means that the combination of attributes A1, A2, and AM must be unique in the table, ensuring no two rows have the same values for these columns. Unique primary key, unlike a primary key which cannot contain null values, candidate keys enforced by the unique constraint can contain nulls. However, remember that null values are treated as distinct, so multiple rows can have null values in a column with a unique constraint as long as the non-null combinations are unique. The check clause specifies a predicate, a condition that must be true for every row in the table. If the condition isn't satisfied, the data cannot be inserted or updated. Let's say we want to make sure that semester column in a section table can only have one of the four values: fall, winter, spring, and summer. We can enforce this with a check constraint, like check semester in fall, winter, spring, and summer. Here, the check constraint ensures that any value inserted into the semester column must be one of these four values. If someone tries to insert values like an autumn, the data will reject it. So this is for today. We will learn about referential integrity, cascading actions, and referential integrity, and all this in our next video. Thank you.